Everyone. Very great to, now I have to say what I want here. Yeah, share the screen. And now my question is, can you see my screen?
We see your screen, but we don't.
Excellent.
Now we see your presentation. Good. Go for it.
All right. That's good to hear. So great to, as well, I wish I could see you all, but it's great to see so many people tuning into this. So I will try to do a good job at giving you an interesting presentation. So my title of my talk is Understanding Intelligence with the Multi-Level Cognitive Architecture. Now, what do I mean by that? Now, we've all heard about David Marr and his 3 levels. And I would like to argue that actually Marr's 3 levels have been misleading us a little bit, because computational level, what's the intelligent behavior, implementation, how is it implemented, but then the algorithmic level of, that is where it happens. And that has given us, and I'm guilty of that too, the idea that we have to find a sort of sweet spot, the place where we can model cognition. So we're all after the cognitive architecture that will do everything we want. And the question is that really the best approach? So, but if I look at computer science and if you look at computer architecture, they have many levels of abstraction. It starts with transistors, and we build logical ports and micro architecture levels. And I mean, this is even from a very old textbook. So maybe there's an even larger set of levels in modern computer architecture. And what I find interesting too here is that anything is digital above the transistor level. So we start with digital very early on. And then the question is, what are the levels of cognition? Now, John gave us of course, on day 1, the Alan Newell's levels. But the question is how to properly instantiate those and how to materialize those, and also how to connect these together. So if you look at computer architecture, every level can perfectly be reduced to the level below it. Now, if you look at nature, that is more or less so, but it's a lot harder to do because it's not engineered. The question is, how does it work in cognition? How do we get from the brain, which is sort of an analog learning machine, to cognition, which is maybe partially analog and maybe, well, I wouldn't call it digital, but let's say symbolic. And we also have learning. And what are levels of abstraction in between? Now, I've come up with a proposal for that, and it looks very complicated, and it's this whole figure here. This is one version of it. And of course, this is bad presentation habit to throw something like this at you. But don't be afraid, I'm going to zoom in on one aspect of this. Now, just to start us off, we are actually already working on a couple of these levels. So many people are working with clusters of neurons. How can neural networks perform skills or learn things? And that's at a fairly low level. And then sort of the red bands is usually what we do with, most of our cognitive architecture. So if I take, for example, XR, then what we do is we write production rules. So that's sort of the middle level here. And we use productions to model tasks. So that's the top level here. Now, I would like to argue, and this is the sort of the topic of this talk, is that we need a level of abstraction between operators or production rules or whatever you want to call it, and tasks. And that is a level I call skills here, for maybe lack of a better term. So what is a skill in this sort of diagram? Now, a skill is you could say a collection of operators or collection of productions or whatever your basic units are that perform things. And it's a collection of operators that performs some sort of reusable cognitive function, some sort of useful skill. And how can it do that? That is by defining a skill, or actually of course, it needs to be learned in some fashion. We don't want to program everything. But the skill also has a number of variables that we can instantiate to actually perform a task. Now, what's the great thing about this is that in many cases, we can do totally novel tasks without any actual learning. So here is an example, maybe you've seen it before because I've used it in presentations earlier. And these are sort of small little tasks and they're for children to perform. But if we as adults look at these sort of little puzzles, like which mother bird has 6 babies, or which animal eats meat, or how many spoons do you see? These are for us novel tasks, but nevertheless, they are fairly trivial to solve. So we don't need any actual learning, but it's also not something that we've done before in this situation, unless you've listened to an earlier presentation of mine, or whether you actually have the game that these puzzles are from. But what we do is that we compose a number of skills that we already have. So if we have something like which mother bird has 6 babies, we need a skill that makes some sort of identification. It needs a skill that does some counting. And there are sort of visual processes involved, and we combine those, and then we can answer that question. And similarly, and this is sort of what this diagram illustrates, we see that these different tasks, they're indicated by stars in the diagram, what we do is we activate a number of related skills, and connected to each of these skills is a set of operators or production rules. Those are represented here by circles. And there's a big overlap in these so that it's clear that we can use a single skill for multiple purposes. Right, so that's of course a nice diagram, but can we actually model data with it? Now, we have very little research in which we toss new tasks at people at where we toss multiple tasks at people. But there is a paradigm like that, and it's called rapid instructed task learning. And this slide shows you a little bit of how that works. What it's like is that people see an instruction on their screen, and it consists of 3 words. So it's something like same, sweet, and left index. And they are taught that they should interpret this in a certain way. And that is on the right, that if you see same, sweet, left index, you have to interpret that as, if the answer is it sweet, is the same for both words, then press your left index finger. And then after people have studied this instruction, they actually see the 2 words. So they see, for example, grape and apple, and then they have to be ready to immediately do this task because they have limited time to give an answer. So they have to prepare a new sort of task given these 3 words, and then they actually see words and they have to do the task. Now, each of these 3 words, so same here in the example, same, sweet, and left index, are from a set of 4. So there are 4 possible words that like same. So second is this in the second example. There are 4 possible attributes and the 4 possible fingers that you can press. So just to see whether everyone is still awake and not checking their email or doing other stuff, well, let's see an example. So I'll show you an instruction and you can sort of mentally prepare, and then I'll show you 2 words and you have to do the task. So here it is, just 1, loud, left middle. So a couple of seconds to prepare, all prepared. Now, normally in an audience, you could raise hands and do stuff, but unfortunately that's not the case. So we see, now you have to wait for the stimulus, and here's the stimulus, drums and mice. Now you can raise your hands whether or not, or with what finger to push, but this is a yes answer, so we have to push the left index. Was it left index finger? I've already forgotten my own instruction. Well, you get the gist. So if we do this task, what do we need to do? Well, we need a couple of skills. So we need a skill for doing these kind of judgments, like same, just 1, or second or not second. Those are the 4 attributes. We also need a skill to test attributes, to test whether something is loud. So this sort of involves some sort of semantic retrieval. And then we need skills that can push buttons. And all these things are things we have to instantiate once we're given an instruction. So an instruction for same, sweet, right index or left index might look something like this, where we say like, oh, we have the same skill. And we need to know what we need to compare in the same skill. In this case, that's the same. We have to do that by determining attribute suite, which is sort of a separate skill that we instantiate with suite. Then we need to tell it what to do in case of a yes response and what to do in case of a non-response. And in this case, it's pushing buttons. And so what we need to do is we need to create this sort of small structure based on the instruction on the screen. And what it looks like in the model I've created, which is, it's a model built in the PRIMS architecture, which is a sort of, you could say, elaboration on Actar. So it's very similar to Actar. And what we need to do is just build these 4 chunks. So what the model needs to do, it looks at these 3 words and it builds these chunks. So it builds just one chunk that points to a determine attribute skill, a press finger yes skill, and a press finger no skill. Those are again 4 chunks that also instantiate. Determine attribute tells us what the attribute is that we need to check. Press finger yes, it tells us what finger to push, and press finger no tells us what other finger to push. So what the only thing the model needs to do when reading the instruction is create these 4 chunks. This is, of course, assuming that it already has the prerequisite skills, otherwise it cannot do that. So it needs a skill for just one, it needs a skill for determine attribute, and it needs a skill for press finger. And it looks a little bit like this. So it has these implementations for the component skills. And of course, it also needs a skill to build the declarative structure that serves as a task representation. So that's the model. And now we can see whether this model actually can model some data. Now, there are lots of experiments with rapid instruction task learning. One of the disadvantages is that most of these are people get a lot of time to prepare for a task. So it's hard to sort of collect data on that or model data on that. There's a lot of neuroscience data that I don't want to get into. But Cole et al. Did an experiment in 2017 where they actually pushed people for fast reactions. So they got a limited time to study instructions, either 1100, 1900, or 2700 milliseconds. And then after seeing the instruction, they got the stimuli and they had to respond within 1500 milliseconds. Now they had 2 conditions within this, additional conditions within this experiment. Either people got a practiced instruction, so an instruction, a particular set of these 3 words that they have seen over and over again before, or they could get a novel combination, a combination they hadn't seen before. And here you can see in the data that they were better at the practice instructions as opposed to the novel instructions. But it's not as if the novel instructions were impossible to do. They were just a little bit less accurate on those. So the model challenges are, well, how to get the model fast enough to do this in a limited time available. Obviously, it needs to already know these skills, but it also needs to accumulate reusable building blocks. So you saw that based on the instruction, the model has to create 4 chunks, but if it already has built these chunks before, it might be able to reuse certain of these chunks. So and of course, if it is a task that it has done before completely, it can reuse the whole structure again. So there is the benefit for that model. So if you run the model, you get here the results. Model are dashed lines and data are solid lines. So you can see that the fit is not totally accurate, but for me, the main challenge was to sort of get in the right ballpark and to get a model fit of these data that is that sort of provides a plausible picture. I guess if I spent a lot more time on it, I could do parameter tweaking to make this fit a little bit better. But I want to move on now to the second example I want to give, and that is sort of, you could say, part of a more general agenda, because here, in this particular example, I built the skills that are needed for the RITL task. And an interesting question is, can we build a sort of more general purpose skill library? that we can use to model many different tasks, so that we can say like, well, here I have some sort of general working memory skill that we can use in many different situations, because this is a very attractive idea, because then we can say, well, we have a, for example, and is going to be my example, a theory of working memory. And working memory is not just a matter of capacity, but working memory is really a set of skills on how to deal with knowledge that we need in the short term. And that can enable us to also build models in which people perform suboptimally. Because I believe that in many psychological experiments where people perform suboptimally, it's not a matter of that we're in principle incapable of doing it, but that it's really that we mobilize the wrong skills to do it. And so I'm going to go over an example of this, and this is an example that has been worked out by my PhD student, Corné Hoekstra. You see him here. And so we're going to look for working memory. Now, there's of course a lot of ideas of chunking information in memory, but if you look at many cognitive models, sometimes they chunk information and sometimes they don't. Sometimes they put every piece of information in a separate chunk. So why choose one, why choose the other? Well, it depends on the situation. So, for example, if we have to remember a phone number, there's lots of data that suggests that we chunk those numbers. But on the other hand, we have a lot of working memory tasks, like complex working memory tasks, where clearly it's very hard to chunk the information, because there's always, in complex working memory tasks, you're given the information one item at a time, and then in between the items you have to do other things. So building chunks there is a lot harder. So it seems like people use separate chunks there. So Corné has built two models, one of a complex working memory task and one of a simple working memory task. And I want to go over those very briefly, because he then used the skills in these tasks to build yet another model. So the simple working memory task is like remembering a phone number. And in these tasks, typically this information is also offered in a chunked matter, so that you see one chunk at a time. So it's like 4 to 9, pause, 6 to 6, 7 2, pause, and then the question is like, which digits did you see? So a typical short-term memory model, so it reads the digits, and once it reaches a chunk boundary, it will consolidate the information as a chunk. So you see 4 to 9, you read those items, and then you build a chunk with 4 to 9 in it. Corné has modeled this using a couple of separate skills, a reading skills, which reads these items and puts them in the imaginal buffer of prims and nectar. And then once there's a pause, a break, it will chunk these together. So it will shelve those away in long-term memory. And then it does that with each of these subsequent chunks. And then at some point, it will retrieve those chunks and report them. So you see 4 skills here: reading, consolidating, retrieving, and reporting. And this model sort of can fit some data from these kind of models, where you see that reporting, there are pauses in or shower reaction times at the chunk boundaries. So you see the serial position curves there at the bottom. Now, then we move on to a complex working memory task where we have to consolidate items separately. So in this case, you see 4, and then you need to do some sort of other tasks. In this case, it's a noun or adjective judgment. So typically you see a couple of these words in a sequence, and then there's another item to remember, like the number 2. And that goes on for a while, and at some point you ask to report the digits. So here, the working memory skill is different. There's of course a noun or adjective judgment, and retrieving and reporting is very similar. So here you see some results of that model where the performance accuracy decreases as the number of items you have to remember increases. Now, modeling these sort of separate tasks was not the main purpose of this project, because now the goal is to say, like, we've got these skills, we've built these skills, and now can we combine them in a novel way for a novel task? Now, it turned out for the task we had in mind, we needed one more additional task, which I'm not going over into detail, and there was a visual search task where The skills are to identify targets and to move attention in the visual field. Now, what Cornet subsequently did is take the skills that we now have built and use them for a new task. Now, the task is attentional blink. And now, if you would be a live audience, I would ask you, who knows about attentional blink? And typically in audiences, most people would know about it. Now, unfortunately, I can't do that, so I'll give you a very brief demonstration, and I hope that most people do recognize this task. So the task here is you see a rapid stream of characters, and they are letters and digits. Now, most of them are digits, so your task is to identify the letters and report them later on, so that they're, well, between 0 and 2 letters in the upcoming stream. Now, I don't know whether this works at all via Zoom, whether you can actually see this kind of a rapid stream, but I'll try anyway. So here we go. Now, normally I would ask you, well, who has seen the letters? And then you would say, I've seen J, or I've seen J and K. And actually the answer is J and K, but the idea about attentional blink is that typically people do see the first letter, but in this case, they don't see the second letter. Now, I have no way to verify at this point whether this movie came across at all, or whether you just saw a gray screen, but well, let's assume you've got some idea about the task. So you see a stream of characters, you have to identify the targets, which are the letters, and most of them are distractors, which are the digits.
Niels, it worked. Niels, it worked.
It worked, great. Well, at least it worked for someone. So we took the skills from the complex working memory task because, well, we asked people to identify letters. So we sort of assume here that people do some sort of single item chunking. So they just chunk the items one at a time. So we need the report skill and the single item chunking. We need the visual search task to identify targets. We don't need to move attention because we keep our attention in the middle of the screen. And we take those 3 skills, reporting, single item chunking, and identifying, and that is the attentional blink model. So we don't need to add anything at all, except sort of tying these skills together in order to get a model of attentional blink. And it turns out this model is actually doing very well at fitting the data. So here you see on top a little bit what the model is doing. So you see the task, there's this rapid stream with a number of digits, then 2 targets, T and A. And the model is looking for targets. Then it identifies the target T. At that start point, it starts to consolidate the T as a separate chunk. And then it misses the letter A, which comes later in the stream, because it only starts looking for targets again when then the next, with the distractor 8. At the end of the stream, it will retrieve and it will report just the T. Now, there's a bit of noise in this whole process, and because of that, it will sometimes be correct because it's done consolidating in time, and sometimes it's not. So you see the data here on the bottom, where lag is the distance between the 2 targets. So the example we've shown here is a so-called lag 2 trial where there is only 1 distractor in between the 2 targets. So the targets are 2 apart. And we see there that the attentional blink is maximum. If the targets are further apart, people also identify them correctly. But if they're right next to each other, that's lag 1, then people also do a good job. And that is because the targets are now consecutive. Instead of consolidating separately, people will consolidate them as a single chunk. So now you might wonder, well, okay, why do people pick this particular skill, the skill of consolidating separately? And why not chunk them all together? And we can do that too. So we can run the model with this different skill choice. We can say like, well, what about consolidating in a chunked fashion? What happens then when we run? 5 minutes? Yeah. I'm almost done. And here you see what happens then. Then the attentional blink is completely gone. Now it turns out that we can create the situation where attentional blink is completely gone. This is an experiment by Falazzo, who said to his participants in a particular condition, instead of saying report the targets, report the letters, he said like, report the syllable that's in the stream. And we assume that saying report the syllable sort of activates a chunking strategy instead of a separate strategy. And that creates the strategy where you chunk the two targets together. And you see here in the data that indeed what Folazzo found was that there was, if you give that instruction, that there is no attentional blink. So to summarize, I talked here about the skill level, which I hope I can convince you that this is a useful level to think about and to try to model, and also to try sort of to identify what kind of skills are common among people and how can they reuse these skills. We do a lot more stuff, and that is, so this is what Corné has done. Attentional blink is the explanation is for the attentional blink, a poor choice of skills, not a limitation of our cognitive system. We also are looking at a much lower level of learning, like how can we learn simple grammatical patterns by a pure bottom-up procedure where we say like, well, we're not assuming any kind of operators or productions to start with, but we have to build them up in a bottom-up trial and error process. And also we want to connect this to sort of neural architecture. So I've been working on trying to implement this low-level strategy in the Nengo architecture. That was my ICCM presentation a year ago for those who attended that. And this is my last slide. So thank you for your attention.
Thank you very much, Niels. Very interesting. We have time for a couple of questions here. David asks, seems like your skill is a lot like the Card-Moran and Newell-Gomes concept of a method, which they defined as a sequence of operators that accomplish a goal compiled from experience and problem solving. Is that relevant?
Absolutely it is. I don't want to say that this is a completely new idea. Actually, a long time ago, and that's also in the Gomes tradition, we of course had the goal stack. And the goal stack is part of many cognitive architectures. It used to be part of ACT-R, but it was abolished. Was it abolished around 2000? Around that time, people said like, well, the goal stack is too constricted. It doesn't fit psychological data. We have to do away with it. It's, and I think that was the right decision at the time, but nothing came instead of it. And I think that was the problem, that it was not replaced by anything else. What you can do with skills is a lot more flexible. It's not like a goal stack. You can move from one skill to another. There is no necessary hierarchy, but you can connect them together as sort of more in a graph-like fashion by sort of instantiating variables that point to other skills. Therefore, it might actually lead to reusable skills, whereas in the sort of traditional goal stack paradigm, that was very hard to do. Typically, sort of these kind of skills were just sort of defined for one particular kind of task.
Good. Okay, Phil asks, can you have skills for creating skills? And this is probably going to be our last question.
That's a good question. I think, well, either skills are created by other skills, which is probably a good idea, but we also need some sort of more bottom-up fashion to create skills. One of these is by association learning. So one of the mechanisms that, of course, I haven't talked about at all is that if you use two operators together very often, they start developing an associative strength between them. So then you say like, well, this might be a useful sequence of operator. And if we can sort of augment the sort of sequencing, then that might be also the key to developing skills. So skills may also sort of develop in like a more bottom-up fashion as opposed to a top-down fashion where one skill creates another skill. Otherwise, we never solve this sort of bootstrapping problem.
Okay, let's give you time for another question. Could a system of composing skills to perform a larger task be applied to language comprehension?
I think language is a very important aspect in this, that what I envision with skills is the kind of compositionality you already have in language. In language, we combine words in totally novel ways by which we create new meaning. And this is something we can generate as humans. We can also understand that if other humans produce it. I think skills should be seen in the same fashion, that we can recombine skills in novel ways to do completely new things. And I think there is a very strong tie-in with language.
Okay. I think there may be one or two more questions on the chat, but we're a little over time. It's time now for a break.